Hi everyone, this is our fifth lesson about limits, and today we're going to talk about asymptotes. So, in Algebra 2 and Pre-Calc, you have learned about horizontal and vertical asymptotes. But today we're going to talk about how asymptotes are best expressed as limits. That's the most precise definition of an asymptote. So, first, let's just look at some graph problems, right? So I'm going to talk first about this problem right here. So this is just reminding us how to even notice an asymptote on a graph, right? So if you look at this carefully, you can see that right here, it looks like we have a vertical asymptote, right? And then it's going to be here that we have a horizontal asymptote, and as well as here that we have a horizontal asymptote. Okay, so this function, if we call this function g of x, what we can see is that the limit as x goes to infinity, right, which means if you were to continue in this direction, going to positive infinity for your x values, it looks like the graph here, right, it's gonna do this oscillation, and it looks like we're settling down closer and closer to this dashed line as our y value. I grant that this graph is not super clear about that. Usually it might be extended like this, and it would be made very clear that as x goes to infinity, the y value is settling down to y is equal to 2, right? And that is a horizontal asymptote. So we can say this is equal to 2. X goes to negative infinity is going this way, right? And you can see that the graph, it does its oscillation and then it's settling down to negative 1 in this case, right? Because this right here is negative 1, and this horizontal asymptote right here is at negative 1. Okay, so notice that it doesn't have to have the same y value in both directions. In other words, going one way, we're settling down to 2, so that's the horizontal asymptote, right? This is the horizontal asymptote at y is equal to 2. Going toward negative infinity, we settle at negative 1, and so we also have a horizontal asymptote at y is equal to negative 1. As x goes to 0, oops, there is also a vertical asymptote here that I didn't mention at first, right? So there's a vertical asymptote right here and right here, right? And you can see that as x goes to 0, we say that y goes to, so x goes to 0, in this case, they're not specifying from the right or the left, so we have to consider both. So x going to 0 from the right, right? You see that y goes down, right? And it's clear from the picture that this graph is not supposed to touch this y-axis, right? This is an asymptote on the y-axis, so this graph will get closer and closer and closer, but will never touch that y-axis. And the same thing on the other side, right? So we can say that in this case, y is going to negative infinity. Overall limit as x goes to 0 is y goes to negative infinity. If you look at the asymptote at x is equal to 2 right here, right? Remember, a vertical line is x is equal to some number. So we've got a vertical asymptote here at x is equal to 2, right here, right? At that point, when x comes in from the right side of 2, right, then y goes to positive infinity. That's up here, right? So this going up here shows us that this answer is positive infinity. And this here, x coming in from the left to 2, right? We're going to negative infinity because the y is going down without bound, we say. So overall, since the right and the left limits are different, this overall limit at x is equal to 2 is a DNE, okay? So that's just a quick overview. How do we look at asymptotes from a graphical standpoint? But let's make that clearer by talking specifically about the limit definition. So when we take a horizontal asymptote, we say that a line y is equal to b is a horizontal asymptote of a graph if either the limit of f of x as x goes to infinity is b, right? Or the limit of f of x as x goes to negative infinity is b, right? And we saw that in the graph example just a minute ago, that both this line up here and this line down here are both horizontal asymptotes, because in the first one, as x goes to infinity, y went to 2, and in the second one, as x went to negative infinity, y went to negative 1. So if either of those two things happens, then we have a horizontal asymptote. Which types of functions have horizontal asymptotes? You might remember this from algebra and pre-calc, but exponential functions have horizontal asymptotes, right? Exponential functions, rational functions have horizontal asymptotes. And really, those are the main ones that we're going to be talking about, okay? And with this new definition, new limit definition out here, we can also say one other thing, and that is that as we saw in the graph up here, the graph of G can actually cross the horizontal asymptote. In algebra or pre-calc, we might often say, well, a horizontal asymptote is a line that the graph never touches. And that's not true, because you can have, a horizontal asymptote. The graph can touch the asymptote, right? But it's a question of what does the graph do as x goes to infinity. As x gets very big, right? Does the graph then settle down and not touch the asymptote, right? So we have to be careful to realize that. Okay, so graph can cross over a horizontal asymptote, as this graph right here is doing, right? So recognize that. Okay, rational functions, that's our main category of functions that have horizontal asymptotes. I'll remind you that there are two forms of the rational function, right? Something that looks like a over x minus h plus k, and then the other form is polynomial over a polynomial, right? So when you look at a function that looks like a over x minus h plus k, the function's going to look something like this right here, okay? And if I'm looking at the limit as x goes to infinity, you have to recognize that that notation right here means what's the horizontal asymptote, right? As x goes to positive infinity. That's going to be this y value right here. So we know that from our pre-calc and from algebra that y is equal to 1 is going to be the horizontal asymptote here. Therefore, this whole limit problem, the answer is going to be equal to 1, okay? This is the same problem with the one just written first, right? So for this answer as well, this is talking about a horizontal asymptote, and that limit will be equal to 1, okay? So let's think about the ones where we have a polynomial over a polynomial. Now here you're being asked again, horizontal asymptote, right? So you look at the polynomial, you make sure you put it into standard form, right? Which means that the powers have to be in descending order on top and on the bottom. So be careful when you rearrange this. This negative sign has to move with the term. And this 3 is a plus 3, right? So I've rearranged it into standard form on the top and the bottom. In this particular case, in all cases, we're going to look at the leading term, right? Leading term means the one with the highest power. And then we're going to look and compare the leading term on the top and the bottom. And when I do that, I'm comparing these two terms. And both of them have a power of 3. That is what I call equally heavy, because the two powers are equal. And the asymptote is going to be at y is equal to the coefficient on top, right, which is this guy of the leading term, divided by the coefficient on the bottom. So this asymptote is going to be at y is equal to negative a half. Okay, and now that you guys are calculus students, you can also look at this function and understand why that happens, right? You can see that as x gets very big, these terms here, x squared and 7, are going to be very small compared to an x cubed term. As x becomes bigger and bigger and bigger, these terms are going to be smaller, much smaller than the x cubed term. So the top function is going to look more and more like x cubed, and the bottom function similarly is going to look more and more like negative 2 over x cubed. And so then the x cubes cancel as x gets bigger and bigger and bigger, and the overall function settles down at negative 1/2, right? So this limit problem, the answer is negative 1/2. Okay, because the limit is asking about a horizontal asymptote, and we know from algebra really that this being an equally heavy polynomial, the limit is negative 1/2. If it were a bottom heavy polynomial, that would be something like, oh, let's say the limit as x goes to infinity of x squared minus 2x over x to the 5th minus 3x squared plus 2, right? So this guy right here would be bottom heavy because the bottom power is greater than the top power. Well, then the horizontal asymptote for bottom heavy is always going to be 0 because as you can see, these terms are going to be minimal as x gets bigger and bigger. The dominant term on top is x squared and bottom is x to the 5th. So that looks more and more like, 1 over x cubed as x gets bigger and bigger. So as x gets bigger and bigger, 1 over x cubed gets closer and closer to 0, right? So bottom heavy polynomials, the horizontal asymptote is at y is equal to 0. And top heavy polynomials, right? If it were, so top heavy would be something like, I could just take the one I just did and flip it around if I had the x to the 5th on top and the x squared on the bottom, right? So these now become very small as x goes to infinity compared to these. So I'm looking at the leading powers, and you can see the top power is 5, the bottom power is 2, right? So this looks more and more like x cubed as x goes bigger and bigger. X cubed is a function that we know does this, right? So it's growing without bound. It has no horizontal asymptote. And with the limit language, we would say this limit is equal to infinity, because as x gets bigger and bigger, x cubed is going to go off to infinity. Okay, so that's how you look at rational functions. Let's see if we want to practice a few more. So I'd like you to pause the video and see if you can figure these out, rational functions. And hopefully you figured out that this one is going to have a horizontal asymptote at 1, whether x goes to positive or negative infinity, doesn't matter with those type of a over x minus h plus k polynomials. It doesn't matter which way you go, the horizontal asymptote is at the k value. This guy here is top heavy, so we're going to be looking at these terms. Function looks more and more like x over 3, so more and more really like a line of slope 3. And so as x goes to infinity, y goes to infinity. If you look at, let's see, this guy, we got to rearrange the bottom and the top really. So we're looking at this. And it looks like bottom heavy. So as x goes to infinity, this is going to go to 0. Here, good to remember that 1 over x as x goes to infinity, 1 over x goes to 0, right? And here we're just making a statement about the hyperbola. This is one of our functions that you should remember and be able to sketch. And you can see that as x goes to infinity there, y goes to 0. Limit of x as x goes to infinity, well, x is just a line, and as x goes to infinity, y goes to infinity, right? So this is going to be infinity. This is a constant, right? And as x goes to infinity, y in either direction, negative infinity. Here, we don't have a horizontal asymptote, but the limit is 5, right? And I put these in here just to show you that, you have to be able to think through something which isn't a rational function either and think whether does it have a horizontal asymptote or not, right? These right here are not horizontal asymptotes, but you should be able to figure out the limit. Okay, exponentials. Quick review on exponentials. E to the x looks like this: 0, 1, 1, e, right? Negative 1, 1 over e. So this is what the graph looks like of e to the x, okay? And you can see that as x goes to positive infinity, y goes to positive infinity. So there's no horizontal asymptote on the right as x goes to infinity. As x goes to negative infinity, y goes to 0, right? Because we have a horizontal asymptote right here along the x-axis when x goes to negative infinity. So this first answer is 0. Any exponential function, regardless of the base, if it's just alone like that by itself, then as x goes to negative infinity, the asymptote is going to be 0, right? 2 to the x is going to look a whole lot like e to the x. It's just going to have a different a growth that's slightly slower than e to the x. So, but asymptote wise, it's going to do the same thing. E to the negative x is a reflection of e to the x, right, across the y-axis. So e to the negative x looks like this, like that, right? And you can see that as x goes to infinity, we're going to have an asymptote of 0. As x goes to negative infinity, we don't have a horizontal asymptote. Something like this, which is 2 to the x minus 1, it's this 2 to the x graph that's been shifted down, right? It's been shifted down by 1. So it's a graph that looks like this. So you should be able to figure out that then the asymptote is right there at negative 1. But I was tricky here, wasn't I? I said as x goes to infinity, right? So 2 to the x minus 1 will go to infinity as x goes to infinity. Let me add that if we were going to negative infinity, right, then this guy would go to negative 1. Okay, let's think about e to the 1 over x. So with this type of problem, we want to be able to think through that as x goes to infinity, it's really a composite function, and I'll talk a lot about composite limits in a couple of lessons from now. But what we can notice is that this function is really going to do, it's going to become like e to the limit of 1 over x as x goes to infinity, right? And we know that as x goes to infinity, 1 over x goes to 0. So this is going to become like e to the 0 or 1, right? So the limit of e to the 1 over x as x goes to infinity is going to end up being 1. Okay, so those were exponentials, right? So we want to know the basic shape of an exponential. We want to know the transformations of an exponential. And from that, we should be able to figure out our horizontal asymptotes. The last thing I want to talk about, well, two more things that I want to talk about with horizontal asymptotes are combinations, right? So when we have functions that are not an exponential nor a polynomial, but they're like a combination of two functions. So you want to think of these. These are often going to be problems where you have a quotient, right? Not always, but often. And when it's a quotient, you want to think about it as a race. I like to think of it as a race. It's really a race between the top and the bottom, because often both of those are going to go to infinity, and it's a question of which function goes to infinity faster. A little bit like the top heavy, bottom heavy idea, but not with just polynomials. So if you look at something like this one, which is supposed to be, let me write it out here again, limit of x squared over e to the x as x goes to infinity, right? So you can really think about this as, a quotient of limits, like we learned from the limit laws. Neither of the limits is 0, right? And so we can at least start to think about it like this. And then you can realize that this one is going to go to infinity, and this one is also going to go to infinity. But this being an exponential is going to go to infinity faster than the quadratic. And so the bottom number is getting bigger, faster and faster than the top number. And so this overall is going to go to 0, okay? When you look at something like ln x over e to the x, ln x grows much more slowly than e to the x. Ln x is the graph that looks like this. It grows actually very slowly. E to the x is the graph that looks like this, which grows very fast, right? So as x goes to infinity, both of them are going to go to infinity, but e to the x is going to go a whole lot faster, right? So if you're dividing the ln by the e, then the whole division is going to go to 0. Cosine x over e to the x, well, cosine always stays between -1 and 1, and e to the x is blowing up, getting bigger and bigger, right? So the division is going to go to 0. In the division problems, if the bottom grows faster and faster, right, like the bottom heavy polynomial situation, same idea, then the quotient will go to 0. Okay, let's look at something like this. E to the x plus e to the negative x as x goes to infinity. Well, we know that this e to the x looks like this and e to the negative x looks like that, right? So if you're adding these two up, you can see graphically the answer is going to look something like that, right? So it's not going to have a horizontal asymptote. Another way to think about it is e to the negative x as x goes to infinity, this guy goes to 0. That's this part, right? But e to the x goes to infinity. So the overall answer will go to infinity. Okay, so combinations, you're going to have to do a little bit of thinking and figure out the answer for horizontal asymptotes. End behavior is the last thing we're going to talk about with horizontal asymptotes, and end behavior is related to horizontal asymptotes. Often there is no horizontal asymptote, and that's what the end behavior tells us, but sometimes there is. So for polynomials, we know that end behavior tells us, do I go to positive infinity or negative infinity? Polynomials never have horizontal asymptotes, right? So you just have to look at the leading coefficient and the power, whether it's odd or even, and from algebra we know that this one goes to infinity, right? I think in algebra we show you how you can have odd and even polynomial, right? And then leading coefficient positive and leading coefficient negative. This guy does that, and this guy does this, and this guy does this, and this guy does that. So from that, you can figure out, just look at the leading term and which way you're going, and you can figure out your answer. This one here, for example, you first have to put this thing into standard form, which means this is going to be your leading term. I have a positive leading coefficient and an odd polynomial, so it's going to do the same thing as I'm going to negative infinity. So if I'm in this situation, but I'm going to negative infinity, then my y value goes to negative infinity here, right? E to the x we talked about as you go to infinity, right? This guy goes to infinity. E to the negative x, we talked about that as well. This is e to the negative x. As you go to infinity, this guy goes to 0, right? So this is really end behavior. I'm repeating myself a little bit with the exponentials, but you just want to make sure that you recognize that horizontal asymptotes and end behavior are related. Cosine x, if you think of that as x goes to infinity, cosine just keeps on doing oscillations, right? So no matter how much you go out there, it's not going to have any kind of settling. It's not going to settle down to any number. Neither is it going to go to infinity. So this we would have to say is a DNE. Same thing with sine x, right? Tangent x as well, because tangent, you might be thinking of the asymptotes, right? It does have asymptotes. But as you go to infinity, you're going through all of these values of the tangent. It goes from negative infinity all the way to infinity, and then it repeats that and it repeats that. It doesn't settle down anywhere. So this has to be a DNE. Let's see, this one's an exponential. E to the x as x goes to negative infinity. This one would be 0, right? So that's horizontal asymptotes. Let's move on to vertical asymptotes. Vertical asymptote is a vertical line. So it's going to be like x is equal to some number. X is equal to 5. That's a vertical asymptote, right? And it's a line where either the limit of f of x as x goes to a from the right side is equal to plus or minus infinity, or the limit as x goes to infinity, as x goes to a from the left side is plus or minus infinity. Reminder, x approaching a from the right side means this, and x approaching a from the left side is that, right? Okay, so which type of functions have vertical asymptotes? Again, rational functions, right? And trig functions, and also the ln or log functions, right? Those are the ones that have vertical asymptotes. With this new limit definition, while a function graph cannot cross a vertical asymptote, a function can be defined at a vertical asymptote. So what do I mean by that? I mean, if you have a vertical asymptote, the function cannot do that. You cannot cross, right? But you can do this. You can have a vertical asymptote here, and you can come in from one side and have actually a function value at the vertical asymptote x value, and then on the other side I might have it going to negative infinity or positive infinity, right? So this graph, if this whole thing is f, it satisfies the limit of f as x approaches 5 from the right is equal to negative infinity. So that means x is equal to 5 is a vertical asymptote. But at the same time, f of 5, right? F of 5 is not a DNE. F of 5 is whatever this y value is. Let me call that 2, right? So just be clear that just because you have a vertical asymptote doesn't mean that the function is undefined at that x value. Okay, how do we deal with rational functions? Well, let's see. Let's start with this one. This is a over x minus minus h, that type of function, right? So we have to do a little bit of thinking here. The top here is 10, and that doesn't change. Whatever you do with the x value, the 10 stays on top. If x is approaching 5 from the right side of 5, right? X is approaching from the right side. That means this value is greater than 5, right? It's getting closer and closer to 5, but it's greater than 5, which means that this overall situation is that the top is 10 and the bottom is a small positive number, and it's getting smaller and smaller positive number. We do this, this kind of notation with two parentheses around for a small number, and it's a number that's not only small, since the limit is all about an approach. As we approach 5, this number is getting smaller and smaller and smaller. So the division of 10 divided by a small number is getting bigger and bigger and bigger, and we can say the limit is infinity. If you're approaching x from the other side, right, so 5 minus, then this number is less than 5. And so we have the situation 10 divided by a small negative number. So this is going to go to negative infinity. Let's maybe pause the video and think through these two, right? So now you're approaching negative 5, and you've got to think about which case gives you a positive number on the bottom and which case gives you a negative number. Pause the video. And hopefully you figured out that here, in this case, if I'm approaching negative 5 from the positive side, right, then I'm at numbers like, negative 4.99, negative 4.999, etc. So this number right here, plus 5, is going to be a positive number. And so this is going to go to infinity, right? If I'm approaching negative 5 from the left side, that's this way, then I'm at like negative 5.0001, negative 5.00001, etc., right? So this number plus 5 is going to be a small negative number, and so I'm going off to negative infinity. Okay, so we have to be able to think through that. Sometimes the thing on the bottom is squared. So you're approaching 3, right? So we have a vertical asymptote because this, vertical asymptote is happening because the denominator is getting closer and closer to 0, right? So in this problem, obviously, if x gets closer and closer to 3, then x minus 3 gets closer and closer to 0. When you square that, though, it's always positive. So this is going to be positive infinity. Okay. This guy here, don't be confused, because the rad x on top, that's x is approaching 3 from the left side, right? So rad x is approaching rad 3, okay? The bottom is getting smaller and smaller. It's actually going to be a negative number squared, but that's going to make a positive number, right? X minus 3 would be negative, but then you square it, so it becomes positive. So this is going to go to infinity. Okay, this guy, careful here not to get confused by the 1, because the 1 is not really going to play into this, because as x approaches 2 from the positive side, first of all, this is one of these a over x minus h plus k type of function. So we know even from algebra that the vertical asymptote is going to be at x is equal to h, right? So we've got a vertical asymptote, and really the question we're asking, we've got a vertical asymptote at x is equal to 2. That's obvious. What we're now asking is, at the vertical asymptote at 2, are we going to infinity or to negative infinity? And what's happening from each side? That's really the question. So if you're coming in from the right side, then this x is greater than 2. The number on the bottom is small positive, right? The 1 doesn't really matter because 3 divided by a small number is a big, big number. And if you add 1 to a big, big number, it's still a big, big number, right? So we're going to infinity this way. On the other side, this is going to be now less than 2. So now you've got a negative number on the bottom, and we're going to negative infinity. So now when this is happening and one side is going to positive infinity and the other side is going to negative infinity, overall limit is a DNE. You cannot say positive or negative infinity. So if I did this same problem and asked you just overall limit, you would have to think through that from each side and say DNE, okay? So be careful with that. A vertical asymptote before, you just, in algebra, you just look at this and go, yeah, there's a vertical asymptote at x is equal to 2, right? But in calculus, this situation would have to be a DNE, right? And that's just saying that it is a vertical asymptote, but we're going opposite directions each way. Okay, we said that log functions have vertical asymptotes, so ln, quick reminder about ln x, right? Ln x, the graph, is just taking the e to the x graph and reversing the ordered pairs, right? So we're going to have 1, 0, 2.7, or e, 1, right? And then it grows like that, and then like this. That's an ln graph. And there's a vertical asymptote at x is equal to 0. So if you're approaching that vertical asymptote from the right, x approaching 0 from the right, then your ln graph is going to negative infinity. Okay, log graphs are the same as ln graphs, except they grow slightly more or less fast. So again, this one is negative infinity. This guy here is an ln graph. You've got to be able to realize that that's an ln graph shifted right. So here's x is equal to 5. The graph's been shifted right. So if you're approaching this from the positive side, then you're going to negative infinity. So you've got to be able to think of the log functions in terms of transformations and figure out asymptote questions. Trig functions. Well, we know that the tangent, secant, and cosecant functions have asymptotes. We know the tangent function has asymptotes at pi over 2 and negative pi over 2, and it looks something like that, right? So we want to be, and then of course at every pi from there. So at 3 pi over 2, we'll have an asymptote, etc., right? This is tan x. We know it's a periodic function. So if you're approaching pi over 2 from the right side, then your asymptote, your y value is going to negative infinity. If you're approaching pi over 2 from the left side, it's going to positive infinity. Overall, we'd have to say that it's a DNE. Even though there is a vertical asymptote, we can only express that vertical asymptote as a DNE. We have to realize that places like pi over 4, there's no vertical asymptote there. So just because you see a tangent in the problem, don't immediately write or think vertical asymptote at x is equal to pi over 4. This is a direct substitution problem. You can put pi over 4 in there and get tangent of pi over 4, which is 1. Secant graph looks like this. We know cosine, secant is 1 over cosine. So the cosine of 0 is 1, so secant of 0 is also 1. And then cosine of pi over 2 is 0. And so you're going to get a vertical asymptote on the secant graph at pi over 2. So that's going to look like this. And then at negative pi over 2, going to have another one. So secant graph is going to look like this. And we know that it's going to do a similar thing here, except the u is going to be downward, right? And then we're going to repeat these u's. And this right here is negative 1. Okay, the top of the u is negative 1 and the bottom of the u is 1, right? So all of this is just pre-calc and algebra review, but you got to be able to think about, okay, negative 3 pi over 2, so I'm at this asymptote. So if I'm approaching from the right of that, then this goes to negative infinity. If I'm approaching negative 3 pi over 2 from the left, then that would be this u over here, and I'd be going to positive infinity. If I'm approaching 3 pi over 2, negative 3 pi over 2, overall it's a DNE. Again, at 0, there's no asymptote, so I just put in secant of 0, which is 1 over cosine of 0, which is 1 over 1 or 1, right? So we got to be able to think through trig function asymptotes like that. Okay, last topic is being able to translate words to equations and invent functions, right? So what do I mean by that? I should be able to take these words. G of x has an asymptote at y is equal to 5 when x approaches infinity, right? So we got to be able to translate this. This translates to that, right? G of x has an asymptote, right? This is a limit. We know an asymptote is a limit, right? And that limit is at y is equal to 5. It's a horizontal asymptote, right? So we have to make that into the limit of g of x as x goes to infinity is equal to 5. That's the math translation of those words. X is equal to 5 is an asymptote of f of x, and it is known that f of x is always positive. Well, if it's x is equal to 5, we know that's a vertical asymptote. If f of x is always positive, that means that on both sides, that vertical asymptote is going to infinity, right? Because f is always positive. So we can say the limit of f of x as x approaches 5 in a vertical asymptote, it's the approach number that's this, right? In a horizontal asymptote, it's the limit. In the vertical asymptote, it's the arrow number. As x approaches 5, the limit approaches infinity. H of x has an asymptote at x is equal to 0. That's a vertical asymptote. So here we can say the limit of h of x as x approaches 0 is equal to infinity. I could say that, but I could also say for this guy, since I'm not told that it has to be from both sides, I could even say something like this, right? That would be okay as well. Okay. F of x has an asymptote y is equal to 0, so that's horizontal when x approaches negative infinity. So limit of f of x as x approaches negative infinity, that's these words, is equal to 0. And the last one, as x gets arbitrarily close to 4, that means as x approaches 4, y gets arbitrarily close to 10. That means y or f of x has a limit which is equal to 10. So the limit of f of x as x approaches 4 is equal to 10, okay? So we have to be able to go between words and math statements. Okay, last one is inventing functions. Sketch the graph of a function that satisfies the given conditions. These questions do not have unique answers. There may be different looking graphs that are all correct, right? So this is a new type of problem which is going to maybe challenge you a little bit, but I think they're really fun. Just first put away the idea that there's only one right answer here. There's an infinite number of possibilities here. But we need to sketch a function that satisfies all the given conditions. So f of 0 equals 0, f of 1 equals 2, f of negative 1 equals negative 2. These are ordered pairs that have to be on the graph. 0, 0, 1, 2, negative 1, negative 2. So start by realizing those points have to be on your graph. The limit as x goes to negative infinity of f of x equals negative 1. This means that a horizontal asymptote, there is a horizontal asymptote at negative 1, and that's just when x goes to negative infinity. As x goes to positive infinity, we've got another horizontal asymptote, which is positive 1, right? And horizontal asymptotes are y equals lines. Okay, so then you just sketch something. You just make your graph, and you say, okay, I've got to put 0, 0, 1, 2, right? So 1, 2, and negative 1, negative 2. So these points have to be on my graph, okay? And then I draw in my horizontal asymptote. As x goes to negative infinity, y has to go to negative 1. So I would recommend that you just draw that here on the negative side, this guy. And then this guy, draw that on the positive side only so that you're not confused about that, right? So we know that the graph has to go through these points. We know also that a graph can cross a horizontal asymptote so long as you get out there means as x gets big, either in the positive or the negative direction, you settle down to the horizontal asymptote. So I'm just going to draw something very simple like this, right? And that satisfies all of the conditions that I've been given. You could have drawn a completely different graph that looks like, I don't know, we could do something like that if we wanted to, and we can do this too. That would satisfy it as well. But the point is, we have to meet all of the conditions that are given to us and be creative with your function, but not too creative. Okay, takeaways. Horizontal and vertical asymptotes are best expressed as limits. By the way, pause the video, do them first, and then check. True or false, a graph can cross a horizontal asymptote. True, like the yellow graph that I just drew. The limit of f of x as x goes to 2 from the right is equal to infinity would represent a vertical asymptote. Remember, the arrow number is a number and the limit is infinity. That's a vertical asymptote. The limit of f of x as x goes to infinity is equal to 2. That would represent a horizontal asymptote. Horizontal asymptotes are related to end behavior. Vertical asymptotes happen when the quotient of a rational, not the quotient, the denominator of rational functions, I would say, get close to zero. They never become zero, but they get close to zero. And trig functions like tangent, secant, and cosecant also have vertical asymptotes because they are defined as quotients. Okay, that's it on asymptotes.